Hi, I wanted to do a video about section 5.7 and 5.8, which are two ideas about inverse functions and then about variation. So I'll explain what that means in a little bit. So inverse functions, it's kind of repeating what we've done before in earlier sections, but it's just looking at power functions and then their inverses, which are the root functions, like the inverse of a square is a square root, inverse of a cube is a cube root. And for some of these, for the even-powered power functions, the main idea in this section is you have to restrict the domain to be only 1/2 of the parabola or 1/2 of the fourth degree polynomial, so that it's 1-to-1 and then it has an inverse. So as an example, I'm taking these from the homework problems, and I'm doing some similar ones that you'll have to do the purple ones for your homework. So number 5, it says here's a function x minus 4 squared, and that's a parabola, but so to make it an invertible function, we have to take the right-hand side of it, just 4 to infinity. And so the inverse, it's easiest if you write it with, instead of f of x notation, write it as y equals x minus 4 squared, solve for y, and then at the end, you get square root of x plus 4 as the inverse function. And one of the key things that we've talked about with inverses is these two functions are going to be reversing because you're just switching the input and output, so the x-axis and the y-axis get flipped. And so the x minus 4 is shifted 4 to the right, and the x square root of x plus 4 is shifted up 4. You can do the same thing for, here's another example where they have f of x is square root of 3 minus 4x. And so if you graph that, that's this purple function over here on the right, 3 minus 4x. And again, you solve that to find an inverse. You solve for the x variable. And when you do that, you get x equals 1/4 3 minus y squared. 3 minus y squared is going to be the blue parabola, but again, we only take the right-hand side of it because the square root, we only take the upper half, the positive side. So when we, one other thing that they want you to see is that the domain and the range of the original function become the range and the domain of the inverse function. They're just exactly flipped. So then they have some real-world applications for this, and I'm going to ask you to do a couple of these, but the idea is the same. So here they have an object dropped from a height of 600 feet. This is the height after so many seconds, and an inverse is just switching. This one is plug in the time and get out the height. So the inverse would be plug in the height and get out the time. And so you have to solve for the time in this equation. And one of the keys that they mention is when you do this, you get a plus or minus as you solve. But in our case, we only take the positive value because time being negative doesn't make sense in our context. And so you get an inverse function here. Plug in the height h and you get out a time t. I'll do one last example of this type of thing. They have a formula for a pendulum. As a pendulum swings, the length of the string that the pendulum is swinging on is related to the time it takes to go back and forth, the period of the pendulum. And here's a formula for it. And if you think about it, this is 2 pi times the square root of L over 32. And so you can think about that as 2 pi over the square root of 32 as a constant times the square root of L. So we're going to see in the next section, in the next little video, this is t varies with the square root of L. The length. And so that's the language that we're going to talk about in the variation of the next time. So meaning the time, the period of this pendulum is some constant, which happens to be 2 pi over the square root of 32, some constant times the square root of L. And so it's proportional to the square root of L. And so we're going to talk in the next video about what that means and how you can kind of interpret that and solve equations. But in this case, all we're supposed to do is express L as a function of t. So that means find the inverse function. And so if you solve that, you get down here, and part of that would be, let me switch to blue, L varies with the square of t. So the relationship in the backwards relationship is if L is proportional to the square of t, or in the first thing, t is proportional to the square root of the length, and so they're backwards in that sense. And so one thing that we're going to talk about in the next video on variation is this idea of in this case over here, if t is proportional to the square root of L, it varies as the square root of L. One way to think about that is if you double L, if you double the input, then you put a 2 inside that, but it's inside a square root. So that changes the time by multiplying by a square root of 2. So if you double the input, the output is only multiplied by square root of 2. It varies as the root of the input, okay? So conversely, with the, in the other sense, with the length being proportional to the square of the time, if you double the time, you put a 2 in, double the time, well, that ends up being 2 squared, or 4 times the length. And so doubling the time increases the length by 2 squared, or 4. So if you talk about it being proportional in terms of the square of the time, that's how you can think about that. I double the time, then the length is actually increased by a multiple of 4.